This lecture is about recursive least squares. As we discussed earlier, we can estimate the unknown parameters of a linear model using least squares in this way. As you know, this is a quite good estimator, but notice that now, say that I have n samples up to time point t, and I'm giving it one more sample at t plus 1. If I have used these measurements before to estimate the unknown parameters, so say, well, let's denote it t to say that this is using the data all the way up to t, and say that I now wish to estimate the new model using the new one sample, like this. What do I need to do then? Well, basically I need to reform my matrices here and recompute the matrix inverse here and form the estimate. This is of course going to be computationally quite cumbersome, especially if I have a large model with lots of data. So this is not desirable. I would prefer to be able to form a recursive solution so that I can just use my earlier estimate that I have here already and update it to this estimate. Given that I only have a single sample, obviously the new estimate is going to be pretty close to my earlier ones. Say that I have 1,000,000 data points and I got one more. The estimate's not likely to change all that much. So what I'm after is some form of expression where I can write the new estimate as my previous estimate plus some scaling, let's call it k. How should I select? What should I scale? Well, the reasonable thing I should assume here is I would want to see what my model can be predicting, and then the part that it cannot be predicting, that is what I would want to be able to feed back. Something like this. Notice that this would be my new observation that I have, my new one sample. This would be my updated regressor, and this would be the estimate that I had up to point t. So this part is what I cannot describe using the model I already have. So it's reasonable to assume that I should scale this somehow to make it in the right dimensions, and I want to then update my previous estimate this way. It seems to be a natural way of updating it. So I have my previous estimate, I want to correct it slightly depending on what the previous model could not handle, and this seems to be a reasonable way to do it. So this is of course what we will end up with, something very similar to this. So let's start. How do I do that? Well, the first thing I do is that I express my covariance matrix estimate R like this as a sum all the way up to t, as well as my XL, YL like this. That means that I can express my estimate in this way. That also means that I can divide my updating of R of t like this. I can take my previous estimate of R of t and just add the last element. And same thing with G of t. This is just the last element. Meaning that if I knew my previous R of t minus 1 or G of t minus 1, I know how to update. So let me begin by exchanging this G of t with this one, so I'll get this form. Then I will use this again and note that I can express G of t in this way, so I will replace G of t here with this. Then I will use the fact that I have an expression for R of t minus 1 like this, and I can replace R of t minus 1 in this way then. Finally, if I multiply R of t inverse in, I will get the previous estimate, some correction factor, and the error that I was expecting to have. Notice that this is exactly what I said before, that I have the measurement, the new measurement y of t, and then the previous estimated parameters like this. And I scale it in some sense like this. One problem with this formulation is that you should notice that I have to compute the inverse of this covariance matrix at each update, meaning that if I have a sample of sequence which is millions and millions samples long, I'll get one more sample, I need to compute this inverse. Then I get one more sample, I need to still compute the inverse. I need to compute the inverse and so forth. And as you know, computing inverses is a very computationally cumbersome operation requiring ordo m cube operations, with m being the dimensionality of the matrix. And given that I'm only adding a single sample, I'm very unhappy with that, because the covariance matrix inverse will of course be very similar to my previous covariance matrix inverse. The way to solve that is to use the matrix inversion lemma. The matrix inversion lemma is a super useful result that states that you can formulate the inverse of a concatenated matrix of this form this way. So by just identifying the A and the B's and the C's like this, I can formulate the inverse of covariance matrix R minus 1, I'll express it as P in this way. Notice that my inverse here is now a row vector times a matrix and a column vector. So this is nothing but a scalar, meaning that I can express the inversion just by a division like this. So let me introduce the so-called Kalman gain, which is exactly this form, and I'll express it this way and multiply this denominator up, and I'll get this form. And finally I got my recursive least squares of this form. So I will take the difference between the observed data point and what my model is dictating. I'll scale it with the Kalman gain, add it to my previous estimate, and voila, I have my new estimate. So the recursive least squares is going to give me exactly the same thing as the normal least squares estimate, but it's formed recursively. So that means that this can also be a very efficient way of estimating the least squares estimate if I have lots of data. However, the formulation has one shortcoming that we would like to address. Typically what happens is that old forms of data are not as relevant as new forms of data. So typically the stock quote of Google 10 years ago is not all that relevant for this current stock quote as the day samples that you had yesterday. So in some sense you would want to add a weighting such that you trust the earlier estimates less than the ones that you have recently observed. The way you do that is that you add a forgetting factor, typically by an exponential forgetting, such that you will trust these estimates less and less. The forgetting factor is selected between 0 and 1, and the closer to 1 it is, the less you are forgetting. So if I have a lambda which is smaller, I will trust only a few samples, but I will trust them a lot, but older samples I basically not trust at all. Whereas if my lambda is larger, I will trust old data just as well, almost, as my current ones. This has the implication that for a large lambda, I have plenty of estimates that I trust reasonably well, meaning that I can average over plenty of them that will take the variance down. Whereas if I have a lower lambda, I will only have a few samples that I'm reasonably trusting, and therefore my variability will go up quite a bit because I only have a few samples that I'm actually trusting. On the other hand, I will adapt much faster to changes in my process. So a lower lambda will adapt faster to a process, whereas a higher lambda will give me less of variability. So a reasonable way of handling this is that you adaptively change lambda as you go along. So if your error between what you cannot handle with your current model is going to be small, you let lambda slowly grow closer to 1. Whereas if this error then all of a sudden decreases, you are shrinking it so that you try to adapt fast to a change. Including this lambda in my derivation will very simply give me the same formulation as I had before, but there will be lambdas popping into the formulation like this. So this is the expression that you normally refer to when you speak about the recursive least squares. Notice also that I'm now introducing in the notation MT here like this way, and this means that I don't have to compute this matrix vector product more than once when I form this expression here. So in general, the recursive least squares is a very good way of forming estimates when you have to take into account changes. But it will only be able to handle AR processes. As you know, if as soon as I have correlated regressors, as I would have in an MA case or an ARMA case, the recursive and the normal least squares will not be able to handle those accurately, then my estimates will be poor. So in those cases, I need to move over to a recursive PEM or a maximum likelihood formulation instead. In this course here, we will instead focus on the Kalman formulation, which will be a better way of doing this.